In the last video, we looked at case 1 of master theorem, which is the scenario where n to the power log of a base b is polynomially larger than f of n, or f of n is polynomially smaller than n to the power log of a base b. In this video, we're going to look at case 2 of master theorem, which is the scenario when both n to the power log of a base b and f of n have the same rate of growth or the same asymptotic complexity. So case 2 is the scenario where f of n is theta of n to the power log of a base b. We could have written this as n to the power log of a base b is theta of f of n. It doesn't matter whichever way you write it. Let's just go with this way. From the definition of theta notation, this implies that there exist two positive constants, C1 and C2, such that for large enough n, f of n can be sandwiched between two constant multiples of n to the power log a. So f of n is lower bounded by c1 times n to the power log of a base b, and it's bounded from above by another constant c2 times n to the power log of a base b. So we are going to use this inequality in the expression for t of n, which, if you remember, was n to the power log of a base b times t of 1 plus the summation of I varying from 0 to h minus 1 a to the power I multiplied by f of n by b to the power I. If f of n can be sandwiched between these two constant multiples of n to the power log a, what can we say about the upper and lower bounds on f of n to the power n divided by b to the power I? If we replace n by n divided by b to the power I in this inequality, which are marked by this star asterisk, we get f of n divided by b to the power I can be sandwiched between c1 times n by b to the power I, the whole thing raised to the power log of a base b, and on the other side c2 multiplied by n by b to the power I, the whole thing raised to the power log of a base b. So again, we are going to try and find an upper bound on t of n Then we're going to try and find the lower bound on T of n, and then we're going to combine both and derive a tight bound on T of n. To derive an upper bound on T of n, we will replace f of n by b to the power I by the right hand side of this inequality, and thereby we will end up with a larger expression such that this overall expression will be greater than or equal to T of n. So we can say that T of n is less than or equal to n to the power log of a base b multiplied by T of 1 plus sigma of I equals 0 to h minus 1 multiplied by a to the power I multiplied by c2 times n by b to the power I, the whole thing raised to the power log of a base b. So we have a to the power I as it is, but instead of f of n by b to the power I, we substitute the right hand side of this inequality. c2 times n by b to the power I, the whole thing raised to the power log of a base b. This means T of n is less than or equal to n to the power log of a base b times T of 1 plus, let's pull out the terms that are independent of I. c2 is a constant independent of I, and n to the power log of a base b is also independent of I. So what's left inside the summation is a to the power I in the numerator and b to the power I, the whole thing raised to the power log of a to the base b. So we will again simplify the denominator by switching the order of the powers. We can write this as b to the power log of b base a and the whole thing raised to the power I. And this is nothing but a to the power I, because b raised to the power log of a base b is nothing but a. Now, if the denominator simplifies to a to the power I, then it's going to cancel out the numerator and we'll be left with 1 inside the summation. So the sum of this series will be equal to h, because you are adding 1 to itself h times. And h we know is log of n base b. We derived this when we built the recursion tree for this recurrence. So we can say that T of n is less than or equal to n to the power log of a base b times T of 1 plus c2 times n to the power log of a base b multiplied by log of n base b. Now among these two terms, the dominant term is the second one because it has this log n factor in addition to this power of n. So we can argue that this whole expression is going to be less than or equal to some constant multiplied by n to the power log of a base b times log of n base b. We have to choose k a bit intelligently, of course. So if we choose k to be some constant value greater than C2, then we can argue that this inequality is going to hold. Let's say we choose k to be C2 plus 1. If k is chosen to be C2 plus 1, then when we take this sum on the right hand side, we will have this function common and the constant coefficient C2 will get subtracted from C2 plus 1. So we'll be left with a coefficient of 1. And we'll need to argue that n to the power log of a base b times log of n base b is greater than or equal to t1 times n to the power log of a base b. So n to the power log of a base b will cancel out on both sides. And we will need to argue that log of n base b is greater than or equal to t of 1. Now that's obviously true for large enough n. As long as you have a function of n that's increasing with n, you're sooner or later going to overtake any constant that you may choose. So this holds for k equal to C2 plus 1. And so we can say that t of n is bounded from above by a constant multiple of n to the power log of a base b multiplied by log of n. So we can say that t of n is big O of, sorry, I should have written the other term first. N to the power log of a base b multiplied by log of n. This base b doesn't really matter because we can change the base of the log by multiplying or dividing with a constant number using the properties of logarithms. So the base is not going to make a difference in the asymptotic complexity here. Here, of course, it's important because the power of n, exact power of n, is going to depend on what the value of a is and what the base b is. So anyway, we have proven an upper bound on t of n. T of n is bounded from above by n to the power log of a base b multiplied by log of n. What about proving a lower bound on t of n? To prove a lower bound, we will replace f of n divided by b to the power I by something smaller than it. We know that c1 times n by b to the power I multiply the whole thing raised to the power log of a base b is less than or equal to this term. So if we replace this term by the left hand side of this inequality, we will be reducing the value of this overall expression. In other words, we'll be reducing the value of this right hand side. So T of n will end up being greater than or equal to that right hand side. So T of n will be greater than or equal to n to the power log of a base b multiplied by T of 1 plus sigma of I varying from 0 to h minus 1 a to the power I multiplied by c1 times n by b to the power I, the whole thing raised to the power log of a to the base b, a to the power I multiplied by c1 times n by b to the power I, the whole thing raised to the power log of a to the base b. We can again pull out what's independent of I outside the summation. So this will be equal to c1 times n to the power log of a base b multiplied by the summation of I varying from 0 to h minus 1 of a to the power I divided by b to the power I log of a to the base b. Now we already calculated what the value of this is. This is nothing but 1 because the denominator simplifies to a to the power I. And so numerator and the denominator cancel each other out because the denominator is equal to a to the power I. And so we are left with this multiplied by h, because 1 added to itself h times is equal to h. And we know that h is log of n base b. So we can write this as c1 times n to the power log of a base b multiplied by h, which is log of n to the base b. So we can now claim that T of n is greater than or equal to n to the power log of a base b times T of 1 plus c1 times n to the power log of a to the base b times log of n to the base b. So if T of n is greater than or equal to this plus this, it must also be individually greater than or equal to this. But if it's larger than the sum of two terms, it must be larger than either term individually. So from this we can conclude that T of n is greater than or equal to c1 times n to the power log of a base b times log of n to the base b. This means T of n is in big omega of n to the power log of a base b multiplied by log n. Again, the base here doesn't matter. So we have derived a lower bound on T of n T of n is bounded from below by some constant multiple of n to the power log of a to the base b multiplied by log n, and it's also bounded from above by another constant multiple of the same function. So from this we can conclude that T of n is in theta of n to the power log of a base b multiplied by log n. And this matches our intuition because in the recursion tree, if f of n and n to the power log of a base b, which is what a to the power h is, if both these have the same asymptotic complexity and each of these terms is the same as this term, right? What is a to the power I times f of n by b to the power n? Well, we saw that it got simplified to c1 times n to the power log of a base b, right? I mean, it will simplify to some constant multiple of n to the power log of a base b. Assuming that f of n is some constant multiple of n to the power log of a base b. So really what's happening is that each of these terms is, each of the level sums I'm trying to find the recursion tree here. So each of these level sums will be the same except maybe for the last term, which may have a different constant factor. And so the overall uh, complexity is going to be n to the power log of a base b, which is what every term is, multiplied by the height of the tree, which is log n. Another way to say it is, it's going to be f of n times log n. So we have proven case 2 of Master's theorem, which says that if f of n is theta of n to the power log of a base b, then P of n is given by theta of n to the power log of a base b multiplied by this log n factor, which visually corresponds to the height of the recursion tree. This is the value of each level sum, and this is the value of the height of the tree. And because the level sums are constant down the tree, the overall cost of the recursion tree is the level sum multiplied by the number of levels, which is log of n, the height of the tree. In the next video, we will look at the third case of Master theorem.